This is the Science Show with Dr. Dada. It's just so nice, you cannot do without. This is the Science Show with Dr. Dada. It's just so nice, you cannot do without.
Well, good evening and welcome to the Science Show with Dr. Dada here on Jambo Radio Scotland, broadcasting from the city of Glasgow. Tonight's question is deceptively simple. Can a machine be intelligent if it doesn't understand where it is? Now, our starting point is a new piece of research right out of the University of Glasgow called TabPFN-GSA. Well, that's going to be interesting. We're going to unpack what that means in a moment. So what this does is it takes a foundation model designed for tables and helps it to pay attention to geography. Not by rebuilding the entire model, but by giving it spatial context, spatial awareness while it makes predictions. My guests today are Dr. Mingshu Wang, a reader in Geospatial data science at the University of Glasgow, and also we have Deng, a University of Glasgow PhD researcher and the first author of the paper. So we're going to begin with the breakthrough itself. We're going to unpack the problem that they found, how they fixed it, and where this could be useful. Later, we're going to ask the bigger questions, like what is intelligence? What is artificial intelligence? Is it really intelligence? Can we say AI or artificial intelligence is genuinely intelligent, or have we stretched the word intelligent a little bit? Well, we're going to discuss these viewpoint questions later in the show as well. Can intelligence exist without understanding or consciousness? What is consciousness? We're going to kind of give our views on those questions as well. Of course, not necessarily as experts, but at least give our viewpoints on them. Now, again, we're going to talk about what a sense of place might mean for any future super intelligence. You can join us live. You can call in on this show as usual on 0141 530 2787. Once again, that's 0141 530 2787. And it's an opportunity to shout out to our supporters, past and present. This show has been supported by the IOP Scotland, and of course you're listening to the Science Show with Dr. Dada. Now, let's get started. Before we properly introduce our guests and before we properly meet them, we're going to go into our science news highlights. So the first highlight today is quite interesting. We know AI is very hot these days, but also quantum is very hot these days. So it's kind of on the same page, as it were. So this first news highlight is very interesting. It's about a very interesting case of a laptop performing a quantum calculation that needs about 100 qubits or hundreds of qubits to perform. So that's quite interesting. Like, how did they manage to do that? Does it mean we don't need quantum computers anymore now? You know, what kind of laptop was it? Well, to understand what happened there, just imagine what happens when, for example, we've all been there before. You need to copy a file, and then suddenly your USB drive is too small, right? The file is too big, and you're like, okay, what am I going to do now? Then you decide, okay, I'm going to use a zip program. You compress the file, and then now suddenly you can put the file on your laptop. So that's exactly the kind of thing they did. So what they've done is that the researchers at Flatiron Institute and Boston University, they've simulated hundreds of interacting qubits. And of course, if you've been following this show, you'll know what a qubit is. But for those of us who haven't, well, a qubit is the quantum version of a computer bit. So it not only has, 0 and 1, unlike an ordinary bit, it can also represent combinations of 0 and 1 that we call superpositions. And the problem begins when many qubits interact. So if you have one qubit here, another qubit, 3 qubits, and they're all interacting, it starts to become overwhelming for a normal computer to capture all the possibilities, right? So what did these researchers do? Well, they didn't store everything. They used something called a tensor network. And you can think of a tensor network as an intelligent kind of zip file system. And instead of recording every possible interaction, every possible part of the Hilbert space or of the space for the computation, they just looked at the important, they stored only the important part of the relationship between the qubits. And by doing that, it compressed significantly the amount of processing power, the amount of space that's needed to simulate the quantum processes. And that's here's the surprising part. Some of the calculations ran on a researcher's personal laptop. It's not even a research laptop, not a powerful computer that's designed to like a supercomputer. No, just his laptop, and he comfortably ran these simulations. And not only that, the simulations produced correct results. So the theoretical predictions and earlier computer simulations matched the results that were produced by the laptop run version of this thing. So it's quite interesting, isn't it? And the question is, does this now mean that quantum computers are useless? Do we not need quantum computers anymore? Well, not really, no. It just means that quantum advantage is a moving target, right? It's not a permanent finish line. And this is because whenever quantum hardware improves, oh wow, we can solve this algorithm using this number of qubits. Well, classical methods can also improve. And so to beat quantum, or to beat the classical versions, then you have to kind of continue to improve the quantum as well. So my opinion is still that quantum technology is very, of course, absolutely very relevant. In fact, this implementation of the algorithm was quantum technology, you could say, because it was quantum techniques, the knowledge of the quantum systems that was applied, albeit it was a simulation on a classical computer. So, but the moral of the story is, before accepting that a problem requires a quantum computer, we should ask ourselves this question: what can the best classical algorithm do, right? So I'll leave that one with you. Anyway, if you want to learn more about this work, the original paper was published in Science, entitled Dynamics of Disordered Quantum Systems with 2- and 3-Dimensional Tensor Networks, and it was by Simpson's Foundation Flatiron Institute, Boston University. So you can learn more and read more about that in that reference. Fantastic. So now this brings us back to our topic for the day, because today is going to be all about artificial intelligence, AI. Of course, as I said before, AI and quantum, they're kind of, the hot technologies and the hot scientific developments of our time. So let us meet our researchers in the studio. So you're welcome, Dr. Mingshu. Am I saying your name correctly, by the way?
Yes, Mingshu, yeah.
So how do you say it in Chinese?
Mingshu.
Mingshu.
Yeah.
Aha. 非常好. So I'm learning a bit of Chinese, by the way. So we're going to be maybe saying some of the things as well in Chinese, just to keep things interesting. And Rui.
Yeah, that's me.
欢迎你. Welcome to the Science Show.
谢谢.
It's nice to have you here. I'm really excited. This work, I think, is really, really exciting because it kind of helps us to think about what does intelligence really mean? Because, we say it's artificial intelligence. What does it need to be truly intelligent, right? So this aspect of geospatial awareness is very, very key on that. Okay, so before we go into some of the details, let's get to know you a little bit more, a little bit better. Perhaps you can start with Mingshu.
Oh, yes. So hello, everyone. So yeah, I'm really excited and happy to be here and to share of our collaborative work. So as said, my name is Mingshu Wang. I'm currently a reader in Geospatial Data Science at University of Glasgow. My research itself combines geography, artificial intelligence, and urban science. So what I have been doing and trying to do is to bring in the geospatial knowledge or geographic knowledge into the kind of artificial intelligence system, so that the geospatial processes, the neighborhood, and the proximity can be better understood.
Fantastic. Thank you very much for that introduction. And can I also ask, we'd like to know a bit more about your background as well. So, where did you do your school, your early school, and what interested you in science? How did you get to be working on this? Just in a nutshell, just briefly.
Yeah, so I did my undergraduate studies at Nanjing University in China, and then I moved to United States for my first master and then PhD, both in geography at University of Georgia.
Wonderful. That's great. Thank you very much for sharing that with us. It's interesting. We'll come back to that in a moment. I just love to, it's nice to hear people's trajectories, how they started, how they first maybe came into contact with what they're working on. So you've been very much a geography person, like hardcore. It's interesting to see. So how did you get into AI then? Is that very much at the higher level of your career, or did you get interested in more in computer science side of things earlier on?
Yeah, so I started as my undergraduate in more like the regional planning and management.
I see.
And then at that time, I realized that the GIS, which stands for Geographical Information System or Geography Information Science, which provide a suite of useful tool, and then the methodology, let's say, to understand spatial pattern and to explain the phenomenon across space, and also to predict the things that I'm interested in across space and time. And then I gradually realized this is kind of the methods. This is the family of the methods. I'm interested in learning more about that, so that I went to United States and then studied for first master, because at that time I didn't thought that clear enough that should I pursue a PhD. But after the master studies, and then the answer was kind of crystal clear that okay, I want to continue this path.
That's wonderful. 非常好，谢谢你跟我们分享。So what about you, Rui? So what was it like for you? Where did you start from? Where did you get interested in working in something to do with geography or even AI, would you say?
Yeah, so I am currently a third year PhD student here in Glasgow. So I think I've been doing GeoAI science for roughly like 5 or 6 years for now.
I see.
So my interest began, I think, back in 2020, the summer. So I watched like a lesson delivered by Dr. Feifei Li, who is like an AI scientific in Stanford University.
I see.
So, so that lesson I think was originally about computer vision.
Wow.
But I thought I was quite interested in it. So I learned kind of some of the basics knowledges about AI and data science.
I see.
Yeah, so I think that's where my research interest begins.
Wonderful. Yeah. I see. And your early school, was that in China? Did that take place in China or was it somewhere else?
Yeah, so that was from China. So I did both my bachelor's degree and my master's degree back in China.
In China. Oh, yeah. Wonderful. Amazing. Good. Yeah, it's really nice to get to know you, both of you, a bit better. So now let's go a little bit into the subject of this research that you've done. So now, when it comes to geospatial data, what would you like to tell the general public about it? Why is it important, and what is it? Why is it a problem for AI, would you say? In other words, what problem did you find that your result solved, would you say? Perhaps we could start with Roy.
So I think our research began with like a tabular foundation model. So just like just like ChatGPT, which is a language foundation model.
Mm-hmm.
So we realized that it's like a ChatGPT moment for tabular data.
I see.
Yeah. So, but we recognize that this foundation model treats like spatial coordinates just like same. It's just like other ordinary features within the table.
I see.
Yeah. So we'd like to know if it can handle or it can properly understand the geospatial aspect of the tabular data, and it can understand the underlying geographical structure.
Wonderful. So there's a few things to unpack there. That's so interesting to me. I'm like, wow, okay, a ChatGPT moment is quite a nice way to put it. So if we kind of backtrack a little bit, so what is a foundation model? Just for those of us, the people who listen to the show, a lot of us are very interested in these concepts. Maybe they've heard it before, but it was nice to hear it from someone who actually works on it, right? So would you like to explain to us, perhaps, Dr. Wang, what is a foundation? How would you explain that in a very simple way?
Okay, I will try my best. So my understanding of the foundation model is this is a pre-trained model that based on a large variety of the data sets, which has kind of the different kind of the aspect of the data and different topics and different volumes, and they pre-train that and then pack it all together. And then it's already there, so that whenever the users that you want to use it, so they just provide the context, provide the kind of the new data, and then it's automatically kind of give the inference without that the user to kind of reinvent the wheel or restart from the scratch to do all the heavy lifting, kind of the processes themselves.
I see. Interesting. So are there any applications already for these kind of tabular based foundation models that maybe people are aware of that we could use as examples? So we know ChatGPT is quite popular, right? People know, that's what a large language model is. It's text based and so on. For tabular, the tabular version of that, are there any examples that are popular or are these very much still quite kind of research level models?
Yeah, I think that from the kind of tabular foundation model, kind of I think a famous example is the work that our work is built upon. It's the TabPFN. Which is like a general purpose kind of the tabular foundation model it's fit for any sort of the tabular data. So the tabular data is just like a spreadsheet that each row is kind of a record and a observation of things.
Yes.
And then each column represent different characteristics.
Yeah.
And this is quite common type of the data that we experience in our kind of the everyday life.
Yes.
And in terms of another example is that the Google, within the Google, they kind of produce some prototype of the population-based kind of the geospatial foundation model.
Yeah.
And then they release that, I can't remember exactly, something last year and then some updated version this year. The idea for them is that they take all the available data, that Earth observation data, and then the census statistics data that you can think of, then all together and then package them into their foundation model with the idea that if we want to know the information about the neighborhood or county at any US kind of the units, then one can use their model as a zero-shot model just to give you the reference and give you the prediction automatically.
Wonderful. Great. It's nice to relate it to Google Maps. That's something people have seen before, maybe used before. So that's great. So now, Roy, I've got a question for you, and if possible, could you explain without jargon, for someone picturing an ordinary spreadsheet? Dr. Wang mentioned, something like an Excel sheet. So, what makes a table geospatial, would you say?
Yeah, so for an ordinary table, a tabular data set, so all we have is random, ordinary features. So different rows are not connected with a coordinate.
Or place.
Place or spatial information. But in geospatial tabular data, we do have this kind of spatial information. So each row is indexed by some kind of a spatial coordinates. So with this kind of information, so different rows are kind of linked and forms together a geospatial structure.
Wow.
So different roles became interacted.
Wonderful. That's interesting to think about, isn't it? Because you're thinking about an AI, for example. We'll jump into the AI aspect. You're thinking about an AI that you can chat with, like a chatbot, like an LLM. But in this case, it's an AI that's basically the fundamental data type that it works with is this kind of tabular structure. And that's quite interesting. It'll be interesting to see how that interacts with things like LLMs. And okay, that's interesting. So now for such a model, why is it a problem if it assumes that each row is independent, when in fact those rows represent, for example, real places? How would you explain that? Perhaps Dr. Wang.
Yes, I think this is a very brilliant question. For clarity, I think our starting point for this particular research is from the TabPFN, kind of the generic TabPFN data.
Yes.
And surprisingly, the generic TabPFN model can handle kind of a great extent of the geospatial tabular data without the kind of the location or kind of the awareness of the geography. I think this is quite positive and kind of happy, surprising result. And then when we unpack that, we find out the generic TabPFN kind of fall short when the data size are extremely large.
I see.
Or when kind of the feature are highly localized, which means that there are some kind of the very abrupt or sharp change just within the very short distance of the features. At those situations, at least what we found, at those situations, that generic TabPFN doesn't work that well. So that is a starting point from our work. So we propose that the TabPFN-GSA. So basically that's to answer the question that what's wrong or what happens or what let me phrase this way. So what are the characteristics of the geospatial data so that we need some kind of not necessarily second look at that, but need to be more cautious about that. One thing I think is, let me give you an example, I think, that to contextualize this kind of the uniqueness of the geographic data. One thing is that, so let's just take the housing price in Glasgow as an example, because we all live in Glasgow. So if you want to know, let's say, the price of one particular property, one way you can do is that you can look at the housing price or historic transaction for the houses close by. The closer the other houses with recent transaction, maybe more kind of provide more information for you to get an educated guess of your property
Yeah.
compared to a kind of house, like say 5 or 10 miles away.
Yes.
Yeah, so this is what we call that the spatial lag in the kind of the outcome variable. That's the observation of one point. It can be kind of with confidence that can be kind of predicted by the observation nearby.
Interesting.
And then another example is that, okay, we are still looking at the housing price for one particular property, but we do not know that the exact transaction price of any properties close by.
Yeah.
But what you know is the information about their neighborhood condition, their neighborhood kind of characteristics, their transport link, their other kind of auxiliary information about the neighborhood. So that you can still use the information close by to make educated guess or predict some proper value of the property price with that particular point. In our words, terminology-wise, we said those are the spatial lag effects in the covariates or in the predictor size. So because of the characteristics of geographic data, exactly as Ray mentioned, that the observations are not statistically speaking independent.
I see.
So I think that's the one of those uniqueness of geospatial data or geographic data.
I see. That's really nice. Thanks for breaking it down so nicely, so clearly for us. Amazing. So now what we're going to do is we're going to take a music break. And when we come back, we're going to get more into the result that was achieved by the team at the University of Glasgow and the collaborators. And also we're going to get into more about AI. So stay tuned. So to take us into the music break, we're going to listen to a track called GeoAI by GeoAI and Tana Musica. And we'll be right back.
Everybody now. Everybody say Joe. Nice, eh? Yeah, Joe to the Joe, my Jojo. Joe to the Joe, my Jojo. You say Joe to the Joe, my Jojo. About it and by the let me see you say Joe. Say Joe. Yo, Joe. Joe. Everybody say Joe, yo, Joe. Everybody say Joe, yo, Joe. I say Joe, yo, oh, Jody, Joe like all night long, Joe till the sunlight, Joe. Yeah, Joe. And the beat at him and Joe. I say Joe titi Joe my Joe titi Joe my Joe. Akwala tunga Joe. Let's go solo. Let me see you say Joe. Say Joe. Everybody say Joe, yo, Joe. I say Joe, yo.
Well, you are welcome back to the Science Show with Dr. Dada, right here on Jambo Radio Scotland, broadcasting from the city of Glasgow. And we've been talking about something very, very interesting. It's all about AI, it's all about geospatial, data science, and all that good stuff. And we'd like to shout out once again to our supporters on this show, both past and present, including the IOP Scotland. And again, a reminder that you can call in and talk to us and, share your opinions with us, ask us questions. And the number to call will be 0141 530 2787. As usual, we're live on DAB, so you can listen in your car. You can also listen and watch us live at jamboradio.co.uk. Also, you can watch the episodes on YouTube when they get uploaded there. So please do catch up with our previous episodes as well. Before we continue our discussion today, we're going to take our second science news highlight. It's quite interesting. It's about AI, right? The first one was about quantum. This one is going to be about AI. So what is it? It says AI, as we know, it's making discovery science much more efficient. More and more papers are being published than ever before. But the question to ask is, what if AI is making science faster, but also harder to trust, right? So that's the twist on this. Researchers have examined 6,957 submissions and 10,389 written reviews at the Journal of Organization Science. So this is for one specific journal, right? So they found out that since ChatGPT's late 2022 release, submission volume rose by 42%. Wow, 42% more submissions. But at the same time, aggregate readability measures declined. So, the quality basically, declined by some amount as well. Now, reviews estimated to contain more AI writing were also narrower, emphasizing theory more and data less. And the team that did this research, they used an AI detector across thousands of texts. So it's not about accusing, the researchers, right? But it's really to show that, first of all, no AI detector perfectly is able to detect the use of AI, and no detector is definitely not perfect for a single document, so you can't rely completely on that. But this study shows something interesting. It of course covers one major journal and it's not about every field of science, but it still gives us some interesting things. And it's more about the incentives, right? The incentives. It's not about the methodology, but the incentives. Because as we know, in scientific publishing and scientific community, publishing more papers is rewarded. So everybody kind of optimizes for that. It's about the number of papers you publish, right? So because AI makes producing these papers more cheap and more efficient, so to speak, it turns out that the natural impact of that is that if you optimize for volume, then maybe that's going to be at the cost of the quality, right? And of course, peer review still depends on scarce human attention. So, I don't know about you, but in many journals, especially journals I review for, the requirement's always been you can't use AI to do your peer review. So there's kind of a bit of an interesting situation there because of that. So you could say that the introduction of AI is basically, it's not really solving a problem. You could say in some measure, at least, it's almost just moving the bottleneck from the writing to the reviewing, because you have more papers, but still, the number of accepted papers is not necessarily increasing because the quality is less, right? So it's just something to think about. It's quite interesting. The paper was published in Organization Science. The title of the paper, More versus Better, Artificial Intelligence, Incentives and the Emerging Crisis in Peer Review. So that's an interesting food for thought there. So it's something that you might want to have a look at. But now we're going to get back into our discussion about, geospatial data science, right? So now let's talk a little bit more about geography, just to give us a bit more context here about what we're talking about. So back to you, Dr. Wang. The first law of geography. near things are more related than distant things. It sounds intuitive, but where can that be misleading? Could you say? You maybe touched about on it a little bit earlier when you're talking about, the example of, looking for the pricing of properties, for example. But would you have anything more to share on that, perhaps to throw more light on this?
Yeah, I think that you mentioned that first law of geography, that things are related to each other. The closer things, they may be more related than the things that are further apart. I think a caveat of that is that the geographical proximity or distance based measure is just one layer of the connection.
One layer, amazing.
And then the things they connected, in particular when we're talking about the social systems, things are connected at multiple layers.
Yeah.
Geography or physical layer is just one layer.
Mm-hmm.
There's more layers, like perhaps like say the culturally, kind of socially, culturally, and then the related to the identity or history, etc., which may not be simply captured just by the geography.
Wow. Historic, I didn't think about that. There's a lot involved, isn't there? The context. Wow, that's amazing. Okay, so just breaking down some of the other sort of technical aspects as well. So Rui, could you tell us what is geospatial sparse attention? Is it a bit for it's like, okay, GSA or something like that? What does that mean? It's like step by step. So someone like, imagine I'm a 12-year-old and I'm like trying to understand, maybe a clever 12-year-old, and I'm trying to understand what this means. How would you explain that?
Yes, so I think in short, this is like a special strategy that we use to help TabPFN to better handle geospatial tabular data, make it more accurate in processing these kind of data. So the word sparse means that we don't need the model to pay attention to all of the data it can look at. Based on the first law of geography you mentioned before, so theoretically I think we just let the model to pay attention to more closer points rather than distant ones. So we believe that closer points carries more information that could be beneficial for local prediction or regression tasks. So basically we divide the whole study region into small grids, and let the model to process each grid at a time. So the model predicts the whole region not at one time, but step by step, but like grid by grid. So when processing each one particular grid, it looks like a closer grid, like only 8 of the neighborhoods around that grid.
I see.
So it pays the majority of the attention to these neighborhood grids. So while it only pays like random a few attentions to distant grids, because we still wanted to understand the global picture of the data set. So I think technically this helps the model to reduce computation as for one good.
Exactly.
But also make it more focused on prediction of a local phenomenon.
That's more relevant. Interesting. It reminds me of the tensor networks thing that we covered in the highlights as well. It's like you're trying to be more efficient by looking at what matters more, and you can. So it's interesting to see that it's not only quantum that's kind of using these similar approaches, but also AI and geography. Geography, it's interesting. I remember in secondary school, geography was one of my favorite subjects for sure. And it's just interesting to see that you can be doing geography, but also so much deep AI, It's quite nice to see how that works. But what's interesting, I think, particularly in this work, this TabPFN. Oh, by the way, what's TabPFN? What does it mean? sometimes you have CNN, convolution, is it convolutionary or something like that, neural network or something like that. TabPFN is probably something to do with networks as well. Anyway, so you didn't modify the weights, but it was at the context level that you made a modification, that changed the context at inference. So why is that scientifically and practically important, would you say? And I mean, could the same principle help other models as well if you applied the general idea, do you think?
Yeah, so as we talked before, so one good thing about this strategy is that it really helps the TabPFN model. Oh, by the way, TabPFN stands for Tabular Prior Data Fitting Network, which is basically a transformer, large foundation model.
Yeah.
So shares the same structure as language models like GPT or Gemini. So they both share the same structure of transformer.
Amazing.
Yeah. So one good thing about our GSA strategy is that it helps the model to basically improve the prediction accuracy of the model, specifically for geospatial tabular data.
Yes.
So and also just like language models, TabPFN also we need to provide it with a context.
Yes.
Like the data points surrounding the data point that we try to get the answer on. So with the size of the context increases, the efficiency of the model to process this kind of information actually decreases rapidly. So we need to find a way to kind of compress the size of the context, but loss as little information as possible, obviously. So our strategy kind of help it to focus on more relevant information.
Interesting.
So I think that's the second point of our design.
Wow, amazing. And Dr. Wang, do you have any thing to add to that?
Yeah, I think pretty much aligned with what Ray mentioned already. It's our strategy is that we did not modify the TabPFN model itself.
Yep.
We did not fine-tune it in any manner.
Yep.
What we did is, as exactly Ray mentioned, is that we, let's say, talk to TabPFN and say, hey, look at for the prediction, for the inference, look at those points or those samples more carefully than the rest of them. I'm using kind of very kind of the layperson's term to describe what the kind of the GSA exactly does. By doing that, if we take an overview on that, the computational kind of the burden for the any machine reduced because the model kind of the intentionally look at some examples locally and then treat them more important than some random examples that further away.
Yep.
And then it increased the efficiency of the model. And because of the underlying data structure of the geospatial data that has the cheat of the kind of the first law of geography mentioned, this is a characteristic of the data. We utilize the characteristic of the data so to improve its performance in terms of the accuracy.
Wow, amazing. It's really, really interesting, honestly. There's a lot of things in play here. It's about accuracy, about speed, memory, and it's when it comes to applications, it's something that I think can benefit a lot of us. In fact, if not all of us, in one way or the other. So perhaps we can talk a little bit about that now. What would you say are the applications? You kind of mentioned some of them already, just to emphasize this aspect. What would you say are some of the applications? Would you say? So perhaps Rui, 你可以告诉我们
当然可以. Of course. We have already tested our method on a variety of topics by now. So that includes, just like Dr. Wang mentioned before, housing price prediction problem.
I see.
Yeah, so basically we can use historical information about each properties and their locations, of course, within the city to better predict its price. So that's one topic. And we also tested the model on topics, I think, including air quality monitoring.
Yeah.
So that's also a classical, I think, geospatial problem. Because I mean, if suppose you have multiple weather stations, so within a space, so each of the weather station could be related to each other, and closer, maybe closer weather station, we would expect to observe more similar situation.
Yes.
Yeah. So our model can do that as well. And also we tested a data set that I think is particularly interesting is an election outcome data set.
Wow.
Yeah, so we used the model to predict the outcome of the US presidential election. Yeah, so that's also a geospatial problem because, you would expect similar behaviors maybe in closer neighborhoods. And also, I think another data set is a poverty estimation data set.
I see.
Yeah, so that's another classic geospatial problem as well.
Wow.
So I think there are just diverse topics that the model could be applied for better prediction.
Wow. Yes, indeed. Fantastic. Thank you very much for that. So,
Thank you.
yeah, a model can become better by learning which context matters. Wow. Now, but does better prediction count as intelligence? Well, after the break, we're going to ask what the word itself, the word intelligence, what does it even mean now? So it's going to be a kind of a perspective discussion, right? So we're going to talk about that. You can call us 0141 530 2787 and we'll discuss the question, can something be truly intelligent if it does not understand where it is, and related questions. But to take us into the break, we're going to listen to a track by Extra Musica entitled Racines, and we'll be right back. Fantastic. So that was Racines by Extra Musica, and this is the Science Show with Dr. Dada right here on Jambo Radio Scotland, broadcasting from the city of Glasgow. Please do call us 0141 530 2787, and it's nice to have you tuning in with us. Of course, you can catch this show live on DAB, and you can also listen on jaboradio.co.uk. So now we're going to talk about this. This is a perspective discussion, right? It's not, we're going to be having this perspective discussion with GeoAI researchers. So we're not necessarily experts on this specific topic, but in fact, it's not. I don't think anyone is an expert on what intelligence means, right? We're kind of still, as humanity, still kind of figuring out what does intelligence actually mean, because we've had to change the definition a bit since the introduction of AI. Okay, so let's see what we can say. So, in one sentence, what does intelligence mean to you? Perhaps you can start with Dr. Wang, and then we'll ask Rui, and then I'll say my bit as well. So let's start.
Well, what intelligence means, I think that's multi-billion pound questions, right?
Exactly.
I think just one perspective of that is that it's I think intelligence is any sort of knowledge,
Yeah.
human knowledge or non-human knowledge, or let's say other knowledge in the world. That's intelligence. But
Yes.
I think probably that's the answer's too stretched.
Yeah, I know. It's not a definitely, again, it's a perspective thing, and we can only, because as we've seen over the last few years, it's a very multifaceted thing, right? Intelligence, But let's see what Roy thinks. What do you think, Roy?
So I also think that's a really big question.
Exactly.
So and also I think the answer might change with the development of AI, especially. So I think that the development of AI really make us to kind of rethink the question, what is intelligence?
Absolutely.
So back then, before the era of large language models, we don't actually expect a machine to be so intelligent. If it can like distinguish handwritings, or to understand like make classifications, that's good. But we didn't expect it to do much more, or even be more brilliant than a person, a human being. But with the emerging of large language models, now it can like act, it can speak like a human, it can make inference, it can like solve a puzzle, or even achieve high score at like math Olympics competitions. So and eventually it will, if you combine AI with robotics, it can actually sense the world and even change the world in some sense. So I think the problem is evolving all the time.
Yeah, it is indeed, very much so. And Jensen Huang, the NVIDIA's founder and president and CEO, I saw a video of one of his interviews recently, and he was so deep in, it seemed so deep in thought, and it was like, intelligence, like until AI, we kind of rewarded things like, IQ tests and, the ability to solve problems or to write code as intelligence. But now we really need to rethink that, because it seems, okay, if a machine can do it, you're like, okay, what really does intelligence mean? Perhaps intelligence should be something more than just the ability to crunch numbers and to quickly, write code, or to generate graphics, or to even speak, And he's like, maybe to him, intelligence is maybe something to do with empathy, the ability to apply, context, and to have that gut feeling, from the experience, human experience, ability to apply that in making decisions, that sort of thing. So it's a very interesting question, absolutely very interesting. And some people have even made comments about whether intelligence can truly be artificial. In fact, some people go as far as saying, actually, there's no AI. It's just human intelligence. The AI is just, the so-called AI language model is just kind of aggregating human intelligence and, kind of expressing it to us back when we ask it things and so on. So it's a very, very interesting question. But anyway, we have to round up now, because it's been a very, very interesting and very full discussion. 很丰富的讨论，是不是？ So very enjoyable. I would have liked to have some more time to say some things in Chinese, but because of time, we will need to wrap it up there. And it's very interesting. If you want to learn more, you can find out more about the paper that the PFN and the GSA. So TabPFN-GSA. If you Google that, you'll find it, I'm sure. And with that, I'd like to say thank you once again to you, our listeners, for tuning in. And this has been the Science Show with Dr. Dada. Definitely we thank Dr. Mingshu and Rui for just joining us and sharing some of these fantastic things with us. And this has been the Science Show with Dr. Dada. And with that, I'd like to say, until next time, stay curious.